All right, so these are our KMT notes, or kinetic molecular theory notes. And what kinetic molecular theory is it is a way to describe the experimental observations of the behaviors of gases. So the word kinetic means motion. So what does the kinetic molecular theory mean? Well, it's how molecules move. All right, so according to KMT, particles of a gas follow 5 different laws or 5 different steps. The first is that gases are composed of a large number of particles that behave like hard spherical objects in a state of constant random motion. All right, so that's the first law, first part of this theory, that they are constantly randomly moving. The second part of this theory is that these particles are moving in straight lines until they collide with another particle or the container wall. Okay, so the way that I like to think about it is it's just whizzing around, going back and forth in straight lines until they collide. And when they collide, they're going to bounce off, which number 3 kind of explains that when these particles collide with each other or the walls, they're going to experience elastic collisions, which means that there's no energy that's lost between the particles. Okay, so I like to imagine gases whizzing around, but they're also, when they hit the walls, they're bouncing off, like a game of pool, like pool balls bounce off the walls of a pool table. Or you can also think about it in terms of a really super old school video game, like the first video game ever made, which was called Pong. And you can imagine that these gas molecules are moving around the screen like they do in Pong. All right, the fourth step of this theory is that the speed of the particles is related to their temperature. So we've already talked about how when particles are heated up, they're going to move faster. When they're cooled down, they're going to slow down. So basically, how fast they're going gives us a relative idea of what the temperature is going to be, and vice versa. The temperature gives us a relative idea of the speed of the particles. All right. The last part of this theory is that the pressure of these gases, the pressure is related to the number and the force of the collisions of gas with the sides of the container. So the more collisions you have and the harder they hit the walls, the higher the pressure is going to be. So like we've already kind of found, the more particles you have, the higher the pressure is going to be. Once these particles are sped up even faster, right, they're moving faster, the force of those particles is going to increase as well. Imagine you are walking into a wall. You could probably walk into the wall and be okay, right? But if you were to run towards that wall, you're moving faster and you hit the wall, you're going to hurt yourself. So it's the same thing. The faster that these particles move and the more of them that are moving, the higher the pressure is going to be. All right, so let's draw the particle pictures that go along with these statements. So number 1, we said gases are composed of a large number of particles. They're in constant random motion. So it's just this idea of gases are constantly randomly moving. All right, the second one is that they move in straight lines until they collide. Well, we've already kind of drawn and seen what this looks like, right? They're going to move in these straight lines until they end up colliding with a container wall. All right, 3, if they hit each other or the walls, well, what are they going to do? Well, if we have these 2 particles that are going to hit each other, what they're going to do is they're going to bounce off, right? These elastic collisions. If the ball hits a wall, it's not going to stick, it's going to bounce off. Same thing with gases. All right, then number 4, we said the speed of the particles is related to their temperature, right? The hotter it is, the faster they're moving, the more lines they're going to get. And then the 5th part of this theory is that the pressure is related to the number and force of the collisions. So the more particles you have, the harder they hit the walls, the higher the pressure is going to be. All right, so really quickly, let's talk about, there's a couple of things that I want to talk to you about that you guys are going to be exposed to in the next couple of days. And I believe that the worksheet that you are going to do next is going to talk about some of these things. So there are 3 different ways that we can measure pressure. We can measure pressure in atmospheres, we can measure pressure in millimeters of mercury, and we can also measure pressure in kilopascals. And it's really easy to convert back and forth from one to another. So typically in here, we're going to measure pressure in terms of atmospheres. And an atmosphere is going to be abbreviated, and its unit is going to be ATM. No, not the thing you take money out of, but when we abbreviate atmospheres, it's going to be the unit we're going to use is ATM. All right. Well, typically, the world around us is considered to be 1 atmosphere, 1 ATM. Like I said, we can convert these units back and forth from one to another. So 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is also equal to 101.3 kilopascals, kPa. So if 1 ATM is equal to 760 millimeters of mercury, and it is also equal to 103 kPa, therefore 760 millimeters of mercury must be equal to 101.3 kilopascals. All right, so those are the 3 different units that we are going to measure pressure in, and we will be learning how to convert back and forth from one to another. The other unique thing that you may have already noticed is that we don't measure temperature in Celsius, really. I mean, we can, but when we are dealing with gases and eventually when we start dealing with energy, we are going to be measuring temperature in something called Kelvin. All right, so when we measure temperature, we use Kelvin. And the Kelvin scale is unique because it never goes negative like the Celsius scale does. Your coldest temperature ever in Kelvin is 0. So it's true absolute 0. Well, we are going to have to learn how to convert back and forth from Celsius to Kelvin. Well, it's really, really easy. Whatever degrees Celsius you have, all you have to do is add 273, and that gives you your Kelvin, right? So 0 degrees Celsius is what temperature in Kelvin? Well, if you have 0 degrees Celsius, you add 273 to it, it's 273 degrees Kelvin. So the temperature in Celsius at which water freezes is 273 degrees Kelvin. All right, so that is the kinetic molecular theory.